Okay, so now we will look at an algorithm called the Girvan Newman Algorithm to do community detection based on neighborhood overlap. So as explained in the previous video, if the neighborhood overlap of an edge is 0, like in this case, u and v do not share any of the neighbors, then what happens is the neighbors of u have to go to the edge to communicate with the neighbors of v. So if that happens, then all the shortest path in the neighborhood of u have to involve the edge uv uh, to go through the for communication to nodes in the neighborhood of v. So as I said, this is like a bridge edge then that is bridging two different communities. Okay. On the other hand, if this edge uv is such that the end vertices share all their neighbors, then it's well within the community. It's not like bridging two different communities. Okay. So the idea is this. So you will find out the neighborhood overlap scores of the edges and remove the edges that have a lower neighborhood overlap score and observe the partitioning of the network into communities, and then use the modularity evaluation as the basis to kind of decide how to partition the network. So we'll see an example to understand this. So given the graph, you use the neighborhood overlap executable jar file I gave you to find the neighborhood overlap scores for all the edges. And once you find the neighborhood overlap scores for all the edges, remove the edge with the lowest NOVER score. And if there's a tie, remove all the competing edges. So in this case, the lowest NOVER score is 0, that's only one edge, so remove the edge 1, 2. So the graph gets divided into communities. So it's partitioned to actually two communities, which are 1, 3, 5, 6, 9 is one community, and 2, 4, 7, 8 is one community. Now using the pairwise modularity scores jar file, you can find all the pairwise modularity scores and then add them up. It comes to 3.95. As I said in the previous video, for exam purposes, you don't need to show the actual math formula. You just identify all the possible pairs and the corresponding pairwise modularity scores from the output of the executable jar file. Similarly, for the community 2, 4, 7, 8, you find all the pairwise modularity scores, add them up. So the total is 3.95 plus 3.39, which is 7.34. So as you do this, you start building a hierarchy. So there are 9 vertices in this graph, and we are always going to assume in all our examples that the entire graph cannot be in one community and it needs to be partitioned to 2 or more communities. In the sense that the modularity score for the entire community for the entire graph put together as one community is going to be lower than breaking the graph into 2 or more communities like this. So here we see 3.95 plus 3.39 is 7.34, and we're going to assume that the modularity score of all the 9 vertices put together as one community is going to be less than 7.34. So it's better to partition the graph into 2 communities rather than staying as one single community. So now what we need to further analyze is whether to stay as 5 vertices together as one community or partition them further. Similarly here for 2, 4, 7, 8. And we are going to do that along again with no scopes. So once we have the individual communities, then you proceed separately for each of them. So here you have 1, 3, 5, 6, 9. So what you need to do is this. You need to find the NOVER scores of just these edges that are part of this community. So which means you should go ahead and remove the rest of the edges which are part of this graph and just evaluate the NOVER scores based on this. So let me illustrate that. I'm going to save this as another text file. So I'm going to remove all those edges that are not in this community. So 1, 3, 1, 5, 1, 6, 1, 9 are there, 2, 4, 2, 7 are not there, 3, 5 is here, 3, 6 is here, 4, 7, 4, 8 are not there, 5, 6 is here, 5, 9 is here, 7, 8 is not there. Again, make sure the cursor is in the last line. So there are only 8 edges, make sure there are 8 edges, yes. Okay, so save this text file. Now run your NOVER executable jar file, and load this particular text file. Okay, so these are the NOVER scores. So for the edge 1, 3, 0.67, 1, 5 is 1, 1, 6 is 0.67, 1, 9 is 0.33, 5 is 0.67, and so on. Okay, good. Alright, so similarly include only the edges that are in this community and find the NOVER scores. So now for each of these communities, remove the edges that have the lowest NOVER score, which is 0.33 for this community. So if you remove that, it's going to become something like this. So 9 is going to get isolated and all the 4 vertices are together. Okay, now if you're going to determine the NOVER scores of these edges, it's going to be all ones actually, because they're connected to each other. So then if you remove the lowest NOVER scores on this partition, which is this partition, it's going to be 0.5. All 0.5 edges are gone, so it's going to be just something like this. So for an edge itself, its modularity score is going to be 1. Okay. Right, so now there's something called a clique, which you may not be aware. So a clique is a set of vertices that are connected to each other. So these 4 vertices are said to be forming a clique because there's an edge between any 2 vertices. In that sense, these 2 vertices also form a clique because there's an edge between any 2 vertices. And in a clique, the NOVER score for any edge is going to be 1 because every vertex, for every edge, all the neighbors are shared by the end vertices. So that's why I wrote all the NOVER scores of 1 for these edges here, similarly here. Okay, so so this is now the second level of partitioning. So if you partition 1, 3, 5, 6, 9, it's going to partition as 1, 3, 5, 6 as one community and 9 as another community. So 9 is on its own. So find the pairwise modularity scores. Again, to find the pairwise modularity scores, you have to use just the original graph. So that's why I said you just find it once. You find all the pairwise modularity scores once and use the scores again and again. So like here, the pairwise modularity score for 1, 3 is 0.546, which is what we already used here. So it's not that you have to feed only this community to the pairwise modularity scores program. So you have to feed only this community only to the NOVER program to get the NOVER scores. But for the pairwise modularity thing, you have to just compute it once and just use the same pairwise modularity scores again and again wherever needed. Okay. Now for a standalone vertex, the pairwise modularity score is 0. Okay, so that means the sum of the pairwise modularity scores for the pairs in 1, 3, 5, 6 comes out to be 3.42 plus the 0. Okay, so we have to decide whether to stop at 3.95 or break that further into these 2 communities. So if you add the two community scores here, 3.02 plus 0, that is still 3.02, which is less than 3.95. So that means it's better to just stay with these 5 vertices as one community rather than partitioning into two communities. Now with regard to 2478, again after you partition 2478, you're making 2 and 8 to be in their own communities and 7, 4 as one community. And the modularity score for 47 is 0.68, which is something you already know from the pairwise modularity score program. So again, I am emphasizing that don't make the mistake of computing a pairwise modularity scores only based on the individual communities. You have to compute the pairwise modularity scores only once in the beginning of your algorithm, and by feeding in the entire graph as input to a pairwise modularity program. Only for the NOVER scores, you have to compute the NOVER scores based on the individual communities. So that means you have to feed in the edge information pertaining only to the particular community for which you have to find the NOVER scores. Okay, so that's what you will be again and again doing. And as you remove edges, the NOVER scores of some other edges will also change. For example, the NOVER score for this edge 1.5 was 0.75 at the beginning, but after you remove the edge 1.2, its NOVER score became 1. Okay, so for 2478, if you break that into communities, you're breaking them as 2 and 8 as separate communities and 0.68 which is for 47. So 2 and 8 is 0 because for a standalone matrix modularity score is 0. So if you break it up, it's going to be just 0.68, which is less than 3.39. So it's better to just stay as with 4 vertices as one community. So this is what we end up now: 13569 as one community and 2478 as another community. Alright, so I have another example here. So you again go ahead and find the pairwise modularity scores of all the edges, for all the node pairs, and then also find the NOVER scores for all the edges. Then remove the edge 26, which has the lowest NOVER score of 0. Then the graph becomes like this. Now if the graph does not get partitioned, you cannot go ahead and find the modularity scores for the communities, because you have to really partition and then start analyzing for modularity. So just redetermine the NOVER scores of the edges by feeding in this edge adjacency list to the NOVER program, and the lowest NOVER score comes out to be for edge 3.5, which is this one, which is 0.17. So remove that edge 0.1 with NOVER score 0.17. So 3.5 is gone. But the graph still stays as one community. So go ahead and find the NOVER scores of all the edges, and you will find 4.5 and 4.6 to have the lowest NOVER score of 0.2. So removing these two edges will break the graph into two communities like this. Okay, so that's the first level of partitioning. So build the hierarchy. So it's going to partition as 1, 2, 3, 4 as one community, 5, 6, 7, 8 as another community. So go ahead and find the possible node pairs and look at your pairwise modularity scores output, and come up with the pairwise modularity scores and add them up. So in this case for 5, 6, 7, 8 it comes out to be 2.87, and for 1, 2, 3, 4 it comes out to be 3.57. So the sum is 6.44. So again, as I said, we're going to assume that it is better to partition the entire graph into two communities, or two or more communities, in this case 2 communities, rather than staying with the entire graph as one community. Alright, so now we need to decide whether to partition this 5, 6, 7, 8 as further into communities or not. Similarly 1, 2, 3, 4. Now if you notice again, 5, 6, 7, 8 is a click, so all the edge NOVER scores are 1, and if you have to remove any edge with the lowest NOVER score, you have to remove all the edges for 5, 6, 7, 8. So that will break them into 4 different communities like 5, 6, 7, 8 on their own. So is that a good strategy? You should look at this. So 5, 6, 7, 8, if you break it up, becomes 5, 6, 7, 8 with all modular scores being 0, then it's less than 2.87. So it's better to stay with 5, 6, 7, 8 as one community. Similarly, for 1, 2, 3, 4, if you go ahead and find the pairwise modularities, if you go ahead and find the node scores of the edges, these are the node scores. So if you have to remove the edges with the lowest node score, you have to remove all the edges with 0.5 as the node score. So that means 2 and 4 will become their own community, 1, 3 will have node score of 1. So the modularity score for 1, 3 is 0.60 based on output of the pairwise modularity program. So that means 1, 2, 3, 4, if partitioned, it will be like 0.6 modularity score for 1, 3, and 2 and 4 have modularity score of 0. So the sum is still 0.6, which is less than 3.57. So it's better to stay together with 1, 2, 3, 4 as one community rather than partitioning. Okay, so this is the end result of this algorithm. So you have found two different communities, or two separate communities, 1, 2, 3, 4. That's one community, and 5, 6, 7, 8 is another community. So these edges between 3, 5, 4, 5, 4, 6, 2, 6 are the bridge edges that are bridging two different communities. Okay, so we'll stop with this.